The question today says that we have two balls or spheres, I think it says on yours, A and B, that are on top of a table, and it's a two-tiered table. So B is on the top of the entire thing, A is about halfway down on this table, and both of them are going to leave the table with equal amounts of speed. Of course, they're going horizontally, but equal horizontal speeds, and they're going to leave the table at the same time. And so the two questions here, and the first is which will hit the ground first, and the second is which will land farther away. And this is basically something you guys already tested in the FET that we started the unit with. Because all I'm really asking you is how does the height of the launch affect the airtime and the range? And that's one of the things that y'all looked at in the FET. Okay, so hopefully you remember from doing it, but if not, we're about to go over it. And again, make sure that you put your answers in My Open Math. After we go over this warm-up, we're going to get into just some more examples for calculations of horizontal projectiles. So if you don't already have out some paper, again, I'm going to encourage you to go ahead and get that out so you can get that stuff copied down. And then we have a problem set 702.2 that will be today's homework assignment. These notes are pretty quick, so you should have a fair amount of time to work on the assignment, and hopefully that means no homework, but again, if not, it will be due by 11:59 p.m. But back to the warm-up. Okay, so in this question, again, we're really just looking at how height affects time and range. And the higher that object is, the longer it's going to take it to hit the ground. That's the same if you drop things from two different heights as well. Remember, the only force acting on these objects once they leave the table is gravity. And that gravitational acceleration will affect both of them in the same way. They're both going to accelerate at a rate of negative 9.8 meters per second squared. So they're going to speed up as they go down. But obviously, if it's higher up, then it's going to be in the air for a greater amount of time. And so I've labeled them A and B, but I also color-coded them. So mine, ball B, is the white one. And it says the white ball, or ball B, is in the air for a longer time because it started from a greater height, and height determines that air time because it's got that much more space to make its way to the ground before it impacts it. Okay, remember also that each second that both of these are falling, they're also moving forward. Okay, so if this ball is in the air for more time, let's say it's moving 3 meters per second when it leaves the table. Then it's going to go 3 meters per second, or 3 meters each second. So let's say each of these is a second. So that's 3 meters, 3 meters, 3 meters, 3 meters, 3 meters. If it has more seconds in the air, that's more time for it to move forward as well. Okay, and so it's going to give you a greater range. If you count these, I lined them up vertically with each other because I have equal speeds. Okay, so this is after, let's say, 1 second, 2 seconds, 3 seconds. This one's on the ground now. 4 seconds, this one gets to go further by 3 meters, for example, if that was the number, because it's in the air for another second. Again, I don't know that those are accurate. In fact, I know they're not for a table. It would hit the ground way faster than that, but just to simplify the image. Okay, so again, your answer here is that ball B, if it's higher up, the height, the greater height you have, the greater air time and the greater range. Okay, and again, that's what you should have seen in the FET as well. Does anybody have a question about the warm-up? No? Okay, or maybe you're going to save it for later. All right, so again, make sure you have that in My Open Math. And again, if you do have a question, make sure that you ask before the end of the period today. Let's go ahead and get into some notes, starting with another calculation. We're going to do 2 calculations today. We'll have a couple parts to this one. I think the next one does too. So we'll get a little bit extra practice in, and then it's really not any different from yesterday, what we were doing yesterday, just some different examples. And then your assignment's going to have even more examples similar to these. This practice problem says Kara does 12.5 joules of work to move a 250-gram dodgeball from rest as she kicks it horizontally off of a 20-meter cliff. We have 2 questions. The first one is find the time it takes for it to hit the ground. And the second question is how far from the cliff will it land? So I'm looking for time and I'm looking for horizontal range. Again, we're going to start by making a table, because when we deal with projectiles, we have to analyze our vertical motion separately from our horizontal motion, because vertically we have acceleration, horizontally we have constant velocity, and of course we're also in two different directions. Okay, so we're going to just fill in what we know into a table. If I were you, you don't have to draw the whole table with pretty rows and everything like that, but at very least make a T-chart. Okay, horizontal, vertical, and then start labeling things. It doesn't have to be pretty, it just needs to keep you organized. Okay, so again, if this dodgeball is kicked horizontally, that means that it's not kicked vertically, because it would have said so. It would have said it was kicked at an angle. It's not. Okay, so that means my initial vertical velocity is 0. Anytime you have something kicked or launched or whatever, fired horizontally, thrown horizontally, your initial vertical velocity is 0. It's not going to tell you that in the question, but you have to fill it in. If you don't fill it in, it's going to look like you don't have enough information. Okay, so make a note on your paper if you need to, but if you have a horizontal launch, whatever, it's going to have a initial vertical velocity of 0. Horizontally, of course, I do have a horizontal velocity, but I don't know what it is. They didn't actually give it to me in the question, so that's going to be something I have to find later on. Okay, but let's go ahead and keep filling it in. The other thing I know about my vertical motion is my acceleration is due to gravity. It's negative 9.8 meters per second squared. I do know that my horizontal acceleration is 0, so I went ahead and filled that in as well, because I know I don't have any horizontal acceleration. But that's actually the only thing I know about the horizontal, is there's no acceleration. The only other piece of information I know is that this ball is kicked off of a 20-meter high cliff, meaning that the ball is going to fall 20 meters to the ground below, giving it a vertical displacement of negative 20 meters. Okay, so that's it. That's all I know. But that's enough to find time. We can solve the first question with just the information in my table by using the vertical side. Just the data on the vertical side is enough for me to find time. So we're going to do that first, and then we'll come back to part B, how far from the cliff will it land, we'll find the range. Okay, so finding time, we're looking for this, and again, time isn't really vertical, it doesn't have a direction, but if we find it with our vertical data, we can also fill it in on the horizontal side of our table, because time doesn't have a direction like that. Okay, I have VI, A, delta y, of course these up here all say delta x, but I have changed in position in the y direction in time. If I look at my equations and I'm looking for VI, TA, and delta x, because that's what's up here, then the one that I see that I can use to solve it in a single step is going to be equation C, okay, on my board. It's also the third one written over there, but it's delta x equals VIT plus 1/2 AT squared. That's what we're going to substitute into. Again, that delta x, or really delta y since we're in the vertical, negative 20 equals 0 times t. That whole thing's going to get crossed off. It's 0. Plus 1/2 times negative 9.8 times t squared. Again, half of negative 9.8 is negative 4.9. So I end up with this. Negative 20 equals negative 4.9 t squared. I want to isolate my variable, so I'm going to divide both sides by negative 4.9, canceling it on the right. And in my calculator, now I'm dividing 20 by 4.9, which is 4.08. Again, that's not my answer because that's t squared. If I want t, I need to take the square root, which is 2.02 seconds. Okay, so that's my air time, 2.02 seconds, and we found that just using the same kinematic equations that we were focused on yesterday. Before we go any further, does anybody have a question about how I found time? No, we're good? You have one?
Yeah. When do you square that? Oh, yeah.
I square rooted it, yeah. Anything else? We're good? Just making sure. Okay. Then let's go ahead and fill that into both sides of the table. Okay, so that again is both vertical and horizontal. There's no direction to time. Okay, so I've got 2.02 on both sides, and now we're going to do part B. Part B is finding range, delta x, which means I'm looking for this value down here. I can't find it though unless I know how fast the dodgeball is going. once it's kicked, and assuming it's kicked. It doesn't say it's kicked. It says work is done on it. Okay, we're going to assume that that work was kicking it. But all I need to do now is figure out how fast it's going. The other information I had in the question that's not labeled here, because first I need to find that horizontal velocity, and I'm going to use the other information, okay, was that there was work done on the ball, and that work was 12.5 joules. So I know how much work was done, 12.5 joules. I know the mass was 250 grams. Okay, and that's it. That's the only other pieces of information that they gave me. However, I also know that work is equal to change in kinetic energy. So that work, that 12.5 joules that was used to move that ball from rest, that means that that ball now has 12.5 joules of kinetic energy. Okay, if you do 12.5 joules of work on something to move it from rest, you have just told me how much kinetic energy it has. Okay, so I know that I have 12.5 joules of kinetic energy now. And I have an equation for kinetic energy that allows me to solve for velocity. Kinetic energy, we learned last semester, Ke equals 1/2 mv squared. Okay, and I have a mass, and I have kinetic energy. I can find velocity. I do have one little problem though, and that is the mass. Anybody know what's wrong with my mass? It's in grams. I have to do a conversion first. Okay, and I know it's been a little bit, that's why I put this up here to remind you. Okay, but your masses do need to be in kilograms. So that 250 grams, I actually need it to be 0.25 kilograms. Okay, or 0.250 if you want to add on the extra digit. So that's my mass for my calculation. If I substitute in, here's my work, 12.5, which is my kinetic energy after I move it, equals 1/2 times my mass, 0.25, times v squared. If I go ahead and solve this, I take half of 0.25, so I have 0.125, and I divide both sides. 12.5 divided by 0.125, that's 100, equals v squared. V is going to equal 10. I didn't show all the steps, but if you work it out, you're going to get a velocity of 10. Okay, that's the velocity that this dodgeball has after the work is done, which means that's the velocity this dodgeball has when it becomes a projectile. Remember, it's not a projectile until I stop touching it. Okay, so if I kick it, it's not a projectile until it leaves my foot and it's no longer in contact. So my initial velocity is 10 meters per second. It's also my final velocity, remember, because we're dealing with horizontal motion, and once my foot stops touching it, there is nothing else happening horizontally to change that speed. So it's going to be 10 meters per second the entire time. Okay, so now I have all my information that I need in order to solve for my horizontal range. You have two options in terms of equations that you can use with your horizontal data. And they're really the same equation. That's C and D on my screen. They both are actually the same thing. This one, D is delta x equals average velocity, Vf plus Vi divided by 2, that's average velocity times time. And C, if your acceleration is 0, C is the same thing. Delta x equals velocity times time plus 0. Okay, so it's just velocity times time either way. Pick one. It doesn't matter which equation you use. You will get the exact same answer because they are giving you the same thing. I used equation C. Delta x equals, here's my initial velocity, 10, times my time, 2.02, plus all this goes to 0. Okay, so when your acceleration is 0, it just becomes delta x's velocity times time. 10 times 2.02 is 20.2 meters, meaning that my range for this dodgeball, it will land 20.2 meters away from the point that it was launched, or the point that it left my foot. Okay. Are there any questions about this particular calculation? It should look really familiar because we did ones just like it yesterday. Good? Okay. Let's take a look at one more practice problem together before you go and do these on your own. This one's about Freddy the Frog. It says Freddy the Frog takes a swan dive from a 13-meter board. He leaves the board at 6.5 meters per second. If his initial velocity is horizontal, at what angle and at what speed does Freddy hit the water? Okay, now you'll notice in this question, it doesn't say at what vertical speed does he hit the water. It doesn't say at what horizontal speed does he hit the water. It says at what speed. If the question doesn't specify horizontal or vertical, it means that it wants the resultant. That's why I wrote that up there. Okay, so if it just says what's his speed, it wants the resultant, which means you have to add your horizontal and vertical together by vector addition. You're going to be making a triangle, okay, at the end once we get both of them. Okay, but before I get to that, let's go ahead and label what we know about this scenario. I know that his initial velocity is horizontal. It says it right here. His initial velocity is horizontal, which means it's not vertical, which means my initial vertical velocity is 0. I do know that my initial horizontal velocity is 6.5. It's right here, so I filled it in. 6.5 meters per second. It's going to be the same the whole time because my horizontal acceleration is 0. Vertically, my initial velocity is 0, and my acceleration will be due to gravity, negative 9.8 meters per second squared. The only other piece of information I know, and this is the same setup we've had, is I know the height is a 13-meter board, which means I know he's going to fall 13 meters down to the water, meaning his displacement vertically will be negative 13. So that's the information that I have. Okay, again, remember, he's leaving the board horizontally. You're going to have this curved trajectory, this parabolic path. He's going to hit the water with some amount of speed that's diagonal. He's going to be moving both forward and down. Okay, and so that's what we're going to be looking for, is that speed at the end and his angle, which means we're really looking for the direction and the magnitude. We're looking for the velocity. I could have just written what's his velocity upon impact with the water, and that'd be the exact same question. Okay, again, we have to find these components though. How fast is he moving forward? I actually already know that one, 6.5. And how fast is he moving down? Because I can add those two together to get this resultant. Again, adding vectors by vector addition really means we're making a right triangle in this case. So that's what we need to find. In order for us to answer this question, what speed, and find that resultant, we have to find these pieces. So here's one of them, 6.5 meters per second, but I need to find my final vertical velocity so that I can find that resultant. Okay, so I have a couple of steps here. I've got to find VF in the y direction so that I can find my speed that he hits the water with. Okay, so that's step one. Find VFY. We need it to get the resultant. If I look at the information that I have here, again, if I'm looking for my final vertical velocity, I only get to use the vertical data. Ignore that horizontal side of the table entirely. I have VI, A, and delta X, or really delta Y, and I'm looking for VF. And if you look at those kinematic equations, we're going to use a different one. We haven't used this one yet today, okay, or this week. We're going to use the second one on my board. Okay, VF squared equals VI squared plus 2 times A times delta Y, technically. Okay, and we're using that one because that's the information we have. We don't have the time. Now, could I find it? Sure. You can find the time first if you want. You don't need to, though. You can find it, your VF, simply by using this equation. If I substitute in, it looks like this. VF squared equals 0 squared plus 2 times negative 9.8 times negative 13. Of course, that 0 is going to go away, but 2 times 9.8 times 13 is 254.8, but we have to take the square root of it. Guys, if I take the square root of 254.8, my answer, as a reminder, is going to be plus or minus something. Y'all remember that? When you take the square root of something, it's plus or minus. What direction am I going here? Down. I'm going to pick the minus one. Okay, so I don't want y'all to be confused when you see this, but it's negative 15.96. Okay, because I have to choose the correct direction for my situation. In my situation, he's going down, so I'm going to choose negative 15.96 meters per second, and that's going to be his final vertical velocity. Now that I know his final vertical and his final horizontal velocity, I can find that resultant, and I'm going to do it by Pythagorean theorem. We talked about this yesterday. We didn't actually do it, but we talked about it at the end of yesterday's notes. So now we're going to do it. Okay, so 6.5 squared plus negative 15.96 squared. Again, that negative really isn't going to matter, is it? Because we're about to square it. Equals c squared. When I square 6.5, I get 42.25. Negative 15.96 squared is 254.7216. Add those together, I get that number, and now I have to take the square root. Okay, so the square root of that 296.9716 is 17.23 meters per second. And if I had just asked you for his speed and I didn't also ask for the angle, we'd be done. Okay, so if I just asked how fast he's going, that's it. But if I want to know specifically his velocity, or if I say at what angle does he hit the water, we have one more step. Okay, before I go to that though, does anybody have a question about how I got this number? Okay. Last step. At what angle and at what speed does he hit the water? The water is a horizontal surface, so I'm going to be measuring my angle from the horizontal down here. Okay, so I've drawn my theta in. I drew it from the horizontal because the water is horizontal, and we're going to solve for this angle. I know all three sides of my triangle, so I can actually use sine, cosine, or tangent. I'm going to go ahead and use tangent, and the only reason I'm doing that is because these numbers are at least less rounded than this one, because I rounded this twice to get to that number. So I'm going to say that the tangent of angle theta equals opposite over adjacent. It's the TOA in SOHCAHTOA. So opposite my angle right here, my angle theta is this 15.96. Adjacent to my angle theta is this 6.5. So that's what I'm going to be doing. Tangent of theta equals 15.96 divided by 6.5. You'll notice I didn't put the negative on here. I don't need the negative here. I'm just using the magnitudes to find my angle. Okay, so if I want to solve for an unknown angle, anytime you're solving for theta, you're going to be using inverse of that trigonometric function. So inverse tangent in this case of 15.96 divided by 6.5. That's what goes in your calculator. If you want to try it out, but please make sure you're in degree mode. Okay, if you take that inverse tangent of 15.96 divided by 6.5, you get an angle of 67.8 degrees above the water. Again, we have to say angle with respect to what? And it's with respect to the water. It's above the water, just like you see it in my picture here. It'd be above the surface of the water. So my final answer from the velocity is this, the whole thing, 17.23 meters per second at 67.8 degrees above the water. Okay, that's my velocity, magnitude and direction. Questions about this? No? Okay, if you have questions, you're about to find out, because for the rest of the period today, you're working on the assignment 702.2 horizontal projectile problem set. It's due by 11:59 p.m. tonight. If you're working through it and you get to one and you're not sure how to do it, please either ask your neighbor or ask me before you leave today. That way you're able to complete the rest of this at home. You guys have quite a bit of time left in the class period, so again, have paper out, work them out on paper. Don't try to do this in your head or on the calculator screen, and make a table to keep your horizontal and vertical data separate. Again, if you have questions as you're working, please let me know.